Dear students, in last class we studied that how the magnetic field intensity varies with x outside the conductor. Outside the conductor, the magnetic field intensity is inversely proportional to the value of x that we have written here. And inside the conductor, the magnetic field intensity is directly proportional to x. That means inside the conductor, the magnetic field intensity goes on increasing from center up to the surface. And at surface, the magnetic field intensity is maximum. From surface, if we go away from the conductor, that is outside the conductor, then the magnetic field intensity decreases with increase in x value. In today's class, you will be learning inductance of a conductor. In last class, we have defined what is inductor and what is inductance. Inductance of a conductor. By definition, inductance is the flux linkage per ampere. Since there are two flux linkages, one is due to internal flux and second is due to external flux. Inductances corresponding to these fluxes are calculated separately with making some assumptions, and those assumptions are current density in the conductor is uniform and relative permeability of conductor material is unity. So just note these points. This we had written previously as L equal to lambda by I. Since there are two flux linkages, one due to the internal flux and other due to external flux. If there are two flux linkages, by this definition of inductance, there will be two inductances, and these two inductances we have to calculate separately. Corresponding to these fluxes, inductances are calculated separately. Assumptions. First one, current density in the conductor uniform. Relative permeability of conductor material is unity. So with these assumptions, now we will calculate the two inductances separately. In that, first we will take inductance due to internal flux linkages. In first year basic electrical engineering subject, you have learned that the flux density B can be written using field intensity as mu h, where mu is called permeability and it is given by mu naught into mu r. So B becomes mu naught into mu r into h. But h value inside the conductor we have learnt yesterday. So we'll replace H by that relationship. What is that relationship? H inside the conductor is I into X upon 2 pi R square. Let us consider the cross section of current carrying conductor of length L as shown below. So now here is the conductor of radius R. Inside that we have considered a ring of radius X, and then another ring outside the ring of radius X, whose radius is X plus dx. Because inside ring radius is X, from inside ring to outside ring the distance is dx. Therefore the total radius will be now X plus dx. We know that if it is direction of current in the conductor, that is current is flowing outward, then the flux will be appearing like circular rings around it, and the direction of this flux can be found by using right hand thumb rule. Accordingly now the flux appears to be anti-clockwise in direction. Now such flux will be set up inside this conductor and outside the conductor also. Here this is current now. Direction of current is given by point. That means current is coming out of the page or current is flowing upward. Here the direction of flux for the current coming out of the page will also be anti-clockwise. Right? If I consider this small distance dx, and the length of the conductor L, then for us it will be appearing like a rectangle like this. Length is L, width is dx. This flux will be passing through this rectangular strip now like this. Because it is circular, the flux is circular. So in this figure, how can I show this flux? I can show this flux in this way. Right? If I know the flux density, then I can calculate how much flux is passing through this small rectangular strip. If the flux passing through this strip is d phi, then for the given flux density B, d phi is equal to B into dx into L, because flux is calculated as flux density into area. Since it is a rectangular strip, dx into L is the area of the strip. The flux passing through a small cylindrical shell of radii x and x plus dx will be d phi equal to B into dx into L. We know what is B. B is mu naught into Ix dx into L as it is by 2 pi r square, since mu r we have taken as 1. Unit of flux is Weber. See, whether I say d phi as flux passing through this rectangular strip or as the flux passing through this cylindrical shell, both mean same. There will be no difference, because whatever the flux is passing through this strip, that same flux will be there in this entire cylindrical shell. Since this flux links only the current enclosed in the radius of x the flux linkage will be product of flux and number of turns. Thus, d lambda is equal to d phi into x by r square. Since Ix by I is equal to pi x square by pi r square, or d lambda is equal to mu naught into Ix upon 2 pi r square into the bracket x square by r square dx. Assuming length of the wire L equal to 1 meter. Linkage will be I have to integrate this d lambda from 0 to r. The total flux linkage means the total flux linkage means the flux linking the entire conductor from inside. That is equal to 0 to r mu naught into I into x upon 2 pi r square into x square upon r square dx. We will take the constant terms outside. Mu naught is constant. Current flowing through the conductor is also constant, divided by 2 into pi into r raised to 4 integration of x cube dx from 0 to r. You know that integration of x cube will be x raised to 4 upon 4. If we substitute for limits, then we get r raised to 4 upon 4. R raised to 4 and r raised to 4 will cancel, giving us mu naught I by 2 pi r raised to 4 into 4, which will be finally mu naught I divided by 8 pi r raised to mu naught I divided by 2, which will be finally mu naught into I by 8 pi. Lambda equal to I mu naught upon 2 pi r raised to 4 x raised to 4 upon 4 0 to R. I mu naught upon 2 pi R raised to 4 R raised to 4 upon 4 minus 0 raised to 4 upon 4. This will be I mu naught upon 2 pi R raised to 4 into R raised to 4 upon 4. R raised to 4, R raised to 4 will cancel, and we will have I mu naught upon 8 pi. Now we can write for inductance of conductor, because we know the total flux linking the conductor. Inductance due to internal flux linkage, let us denote it by L int. Int means internal, will be internal inductance is lambda upon I. Therefore, substituting for lambda as I mu naught upon 8 pi and dividing lambda by I will cancel. We get mu naught upon 8 pi. Since length of the conductor we have considered as 1 meter, this will be the inductance per meter length of the conductor. That is Henry per meter. It is Henry per meter. So we'll write it in box now. L internal is mu naught upon 8 pi Henry per meter. Inductance due to external flux linkages. Now let us calculate the inductance due to external flux linkage. Let us calculate the inductance of conductor due to external flux linkage. Between points A and B. At distances d1 and d2 respectively, from the center of the conductor Let us say now this is conductor here. Outside the conductor, say at a distance of x, we have one ring of radius x, and within this ring and outside this ring we will consider two rings of radii d1 and d2. Say A is on this ring of inside, say A is on the ring of radius d1 units and B is on ring of radius d2 units. The flux density Bx at a distance x from the center of the conductor as shown in figure can be expressed as Bx equal to mu naught into mu r into Hx. Now we have to substitute here for field intensity Hx outside the conductor. If we do that, we get Bx equal to mu naught into I upon 2 pi x Weber per meter square, and we have considered mu r to be equal to 1. It is our assumption, right? Thus flux in the concentric circle shell will be d phi equal to bx into dx into L, that is mu naught I upon 2 pi x into dx into L Webers. Here dx is again the width of the rectangular strip about which I have explained previously while explaining the inductance due to internal flux linkage of conductor. This flux links the current I and thus the total flux linkage between points A and B will be lambda equal to integration of I mu naught upon 2 pi into 1 by x dx, assuming L equal to 1 unit. You can write here unit also. Integrating and simplifying, we get I mu naught upon 2 pi ln of d2 by d1 Weber turn per meter length of conductor. Therefore, the inductance due to external flux linkages will be L external equal to lambda by I equal to mu naught upon 2 pi equal to ln d2 by d1 Henry per meter. We'll write it separately in a box. Dear students, I will stop the class here and continue in next class. Thank you.